In Lesson 2, we talk about some maximization and minimization problems. And what we're going to do is we're going to be having functions that represent something that we want to maximize or minimize. Maybe it's cost, or maybe it's area, or maybe it's profit. And we're going to use calculus to help us find those maximums and minimums. We know what a lot of the graphs look like, and we could graph them to find maximums or minimums, but we also can just use calculus and use the idea of critical numbers. And we remember that maximums and minimums occur at critical numbers. We'll find the first derivative to find the critical numbers, and then we'll use the second derivative to find maximums and minimums. So let's go ahead and jump in. Here's an example for us. It says the function a of x equals negative 3x squared plus 6x plus 2 gives the area of a region in terms of x. Find the maximum area. Well, as you see written here, this is a parabola that's opening downwards, so we know it has a maximum. We could graph it and find the max. We could put it in work form. But what we're going to do here is we are going to go ahead and take the first derivative of this to help us find the critical numbers. And now, in this case, we know it's a parabola facing downward. So we know when we find that critical number, that will be the maximum. So we want to set this equal to 0 to find the critical number. We can add 6x to both sides and divide by 6, and we get that x is equal to 1. We want to find the maximum area. So we know the maximum area occurs when x is equal to 1. So we'll plug that back into our function. And we get negative 3 plus 6 plus 2. So that's 8 minus 3. So the maximum area is 5 units squared. So that was nice and simple. So we found the critical number. We knew what the graph looked like, so we knew that was a maximum, and we plugged that value in. Now we have a word problem here. So it says, Mr. Wallen has 100 yards of fence. He wants to form a rectangular field enclosed on 3 sides by the fence and on one by a river whose banks are straight. Find the greatest area that fence can enclose. So makes sense. You want to enclose a field there or something, and you want the largest area. So we need to come up with an area function here, and then we would maximize it. Well, this total perimeter is going to be, well, not the total perimeter, but the perimeter, the fencing is 100 yards. And so what we're going to do here is we're going to say, well, let's let this represent x. And what will this length be? Well, this length, we have 100 yards of fence, and we already used up x and then another x. So that length there will be the 100 yards, and we're going to subtract the 2x that was already used up for the other sides of that enclosed area. And well, now we can find the area function. So we used the information about how much fence we had to find the dimensions in terms of x, and now area of a rectangular region is x, in this case x times 100 minus 2x. That's negative 2x squared plus 100x. And we want to find the maximum. Again, this is a parabola, so we could put it in work form by completing the square. But we also can just find the critical numbers. So we're going to take the derivative of this, which is negative 4x plus 100. We will set it equal to 0 to help us find the critical number. So we can add 4x to both sides. We'll add 4x to both sides and then divide by 4. So that would be x equals 25. So it says find the greatest area that the fence can enclose. Well, we found that this x is 25. We could do a couple things here, actually. We could put it back into our picture here and figure out the area, but we can just plug it back into our area function. Either way will be fine. So we want the area when x is 25. We can put it into either one of these functions. Looks like the first one might be easier. So 100 minus 2 times 25. Well, this is 25. This is 50. 100 minus 50 is 50. And then 25 times 50 is 1,250. And this was in yards. So the area yards squared. So there you have it. We found the function for area, then took the derivative, set it equal to 0 to find the critical numbers, and then plug that into our area function to find what that maximum area would be. So we actually see here, if we wanted the dimensions, which I don't think it asked for, we have, this would be a 25 yards by, and when you put 25 back in for x, you get 50. So it's 25 yards by 50 yards. Moving on, it says find two positive numbers whose sum is 8 and whose product is maximum. So two numbers whose sum is 8. Well, let's just call these x and y, so we know their sum is 8, so x plus y equals 8. And the product is maximum. Now, realize when we do this, we want a function to find the product, so p of x, and we're going to do this x times something, x times y, so using this first part, that the sum is 8, we can find that y equals 8 minus x, and so our product is going to be x times y, but y is 8 minus x. So the product is going to be negative x squared plus 8. Find two positive numbers whose sum is 8 and whose product is maximum. Sorry, this is 8x. I need to distribute that. And, well, to find a maximum, we can take the derivative. We'll find the critical numbers. So that's negative 2x plus 8. Set that equal to 0. To solve that, we could add 2x to both sides and divide by 2. So x is equal to 4. So our first number is equal to 4. So what does our second number have to be? Our second number has to be 4 as well, because 4 plus 4 equals 8. So the two numbers are 4 and 4. Once again, we found a function, either one of these. This is the second one's the easier one to work with. Took the derivative and set it equal to 0 to find the critical numbers, and then plug that back into the function. Again, a knowledge that this is a parabola facing downward helps us realize that that will be a maximum. All right. I believe this is our last example. It says, make an open-top cardboard box by cutting squares from each corner of a 12-inch by 15-inch piece of cardboard and folding up the edges. Find the value of x that results in the largest possible volume and find the volume of that box. So we want to, these are going to be x, these little squares here, we're going to call these x. And we've worked through problems like this before. The box is going to look something like this, where this height here is x. And so it says this is 12 inches. The whole thing is 12 by 15. Well, when we cut these parts out, what's left, which is this length and this length, will be the other dimensions of this open-topped box. So let's write this in here. This blue part is going to be 15 minus 2x, which means this blue part is going to be the 12 inches minus 2x. So we have those dimensions, and we're doing that because we want to find the volume. And maybe I should have mentioned that earlier. We want to find a function for volume. Well, volume of a box is length times width times height. So we'll put the x first, that's the height, times 12 minus 2x times 15 minus 2x. Here's the 15 minus 2x, and the 12 minus 2x would be this one. So that's our volume. And we want to find the maximum volume. And so what we'll do is we'll multiply this function out, and then we'll once again find the critical numbers. So we're going to get, looks like we'll have 4x cubed negative 24 and negative 30. So I'm doing negative 24x minus 30x. That's negative 54x, but it will be multiplied times this x, so x squared. And then 12 times 15 is 180x. So that is the volume function. Now what we want to do is we want to take the derivative of that volume function, which will be 12x squared minus 108x plus 180. We would set that equal to 0 to help us find the critical numbers. So we have 12x squared minus 108x plus 180. Looks like we can divide everything by 12. So divide both sides by 12. We still have 0. We have x squared. We have 9x plus 15. It doesn't look like this can factor, so we would have to use the quadratic formula. So let's go ahead and do that. We have x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Plugging that in, we have 9 plus or minus the square root of 81 minus 4 times a, which is 1 times 15, all over 2 times 1. That is 9 plus or minus the square root of 81 minus 60 over 2. 9 plus or minus the square root of 21 over 2. Square root of 21 is 4.58. So we wanted to do 9 plus the square root of 21. Should have just done this first. And divide that by 2. And then 9 minus the square root of 21. And divide that by 2. So we have the two answers of 6.79 or 6.8 and 2.2. We have 6.8 and 2.2 are our answers. Well, only one of these we could actually do. If we tried to cut out a 6.8 side, if we try to cut out 6.8, we wouldn't have enough room or enough cardboard to actually have 12 inches, because if we cut off 6.8 and 6.8, they would overlap. There's not enough room. So that answer is not possible. And so we would cut off 2.2 inches from each corner. 2.2 inches, so find the value of x. We found that. And then we would want to plug it back into either one of these would work. So I'm going to go ahead and plug that in. I'm going to go back to the calculator. Hopefully I can remember this. So we have 4 times 2.2 cubed minus 54 times 2.2 squared plus 180 times 2.2. Now this is not going to be exact because that 2.2 was rounded, but we have 177.232. So the volume is 177 inches cubed, and the x should have been 2.2 inches. And there we have it. To find maximums and minimums of functions, we can take the derivative, set it equal to 0. And in this case, we do want to check our answers to make sure they make sense.